Hello everyone. Welcome to this video on distributions of one-to-one transformations. I will do this one in two parts. The first part will discuss distributions of one-to-one univariate transformations. And then as an extension of that, I will discuss about distributions of one-to-one bivariate transformations. So we start with a theorem giving you the way to find the density function of a one-to-one transformation. Suppose x is a continuous random variable with probability density function fx. Let A be the set of x's for which the density function is greater than 0. So that means A is called the support. Assume that y equal to gx defines a one-to-one continuous transformation from A to the set B, where B is set of gx's for which x's are in A. Right? So we are going to consider one-to-one continuous transformations only in this case. The second assumption is that the derivative of x with respect to y is continuous and non-zero for y in this set B. So under those two assumptions, when those two assumptions are satisfied, then y, capital Y equal to g of capital X is a continuous random variable with the density function given by this expression. If X is continuous, Y is also continuous, and the density function of Y can be found using the known density function of X. Right? So Fy is equal to Fx. So this is actually x, but now x equal to g inverse y, right? Where this y is this value, but usually we should not write down this in terms of x because we want to write down the density function in terms of y. So therefore we have to write down this as g inverse y. So that means x has to be expressed in terms of y, and then times the absolute value of the derivative of x with respect to y. So that is the formula that we have to use. We will first derive this formula, right? Because there are certain things that I can explain in the derivation. Therefore, let's look at the proof of this theorem. So here the transformation that we consider is one-to-one. If gx is one-to-one, gx is either monotonically increasing or it is monotonically decreasing. Right? So therefore, we are going to consider these two cases separately and then finally get one equation for both cases simultaneously. Suppose g is monotonically increasing. Then we know that derivative of g with respect to x is positive. That means dy by dx is positive. And therefore, dx by dy is also positive. Now, let us try to derive the cumulative distribution function of y. And then we will take the derivative of that to get the density function of y. Right. So, by definition, the cumulative distribution function of y evaluated at some value y is the probability y less than or equal to simple y. That can be written as probability y can be replaced by g of capital X. So gx less than or equal to simple y. Notice here capital Y is a random variable, capital X is a random variable, y is just a real number. And this one, because because g is monotonically increasing, gx less than or equal to y, if and only if x is less than or equal to g inverse y. So we can easily see this. For example, suppose this is x, this is g of x. Let's consider some, let's suppose this is an increasing function. Let's consider some y value here. And then what is looking at is gx, that is gx less than or equal to y. So that means this region. Gx is less than or equal to x. What is this value? This is g inverse y here. X value here is g inverse y. So y is, sorry, gx is less than or equal to y when x is less than or equal to g inverse y. So that's what this thing means. Right? That happens because g is monotonically increasing. But now we can see that this is the probability x less than or equal to some value. This is a value, real number. So therefore, this is actually the cumulative distribution function of capital X evaluated at this value g inverse y. So that is the expression for the cumulative distribution function when g is monotonically increasing. Now, to get the density function, we take the derivative of this thing with respect to y. So therefore, the density function of y evaluated at y is equal to the derivative of the cumulative distribution function. So that means the derivative of this function that we derived in the previous slide. So when you take the derivative of this one, first of all, we get the density function evaluated at this value. And then we have to multiply that by the derivative of this quantity with respect to y. So that is the application of the chain rule. So therefore, you get the density function evaluated at this value times the derivative of g inverse y. G inverse y is actually x. Therefore, this one more simply can be written as dx over dy. Right. So in this case, dx over dy is positive. This quantity is positive. Everything is positive. So that is the expression for the density function. If a density function of y, if gx is monotonically increasing. Now suppose or consider the situation where g is monotonically decreasing. In that case, dy by dx is negative and therefore dx by dy is also negative. So now let us follow the same procedure. Fyy, that is the cumulative distribution function, is equal to probability y less than or equal to y. So that is the probability gx less than or equal to y. But now gx is monotonically decreasing, right? So we have a situation like this now, x and gx. So the function is decreasing now. So let's now consider gx less than or equal to y. Suppose this is y, right? So gx is less than or equal to y in this region, right? This is where gx is. So if you consider this one, this is g inverse y. So gx is less than or equal to y whenever x is greater than or equal to g inverse y. So therefore, this expression is equivalent to this expression. Right? But now this one can be written as this one is equal to 1 minus the probability x less than or equal to g inverse y. Right? You can still have the equal sign because these are continuous random variables. So this one is actually the cumulative distribution function of x evaluated at g inverse y. So that's why we have 1 minus that expression. Right. So now let's take the derivative of this thing with respect to y to get the density function. So the derivative is going to be derivative of 1 minus fx g inverse y with respect to y. So when you take the derivative with respect to y, first of all, you get this negative sign. And then the density function of x evaluated at this value times the derivative of this quantity, right, with respect to y. Right. So you have negative fx evaluated at this g inverse y. And then this is actually dx over dy. But now remember dx over dy is, that is derivative of x with respect to y is now negative. So that negative sign, negative value, and this negative becomes, when you take the product, it becomes a positive, right? So therefore this whole thing becomes a positive. It has to be because we know this is a density function, right? So therefore, in general, we can write down the two cases in one equation like this, right? Fyy is equal to fx g inverse y. You can take the derivative, the absolute value of the derivative. Right. So therefore, this part will be positive. This is always positive. So this equation will be valid for both cases. So that is the formula that we use to get the density function of a one-to-one continuous transformation of a continuous random variable x. Right. Now let us look at few examples. First example, let x be a random variable which has a uniform distribution in the interval 0, 1. Use the above result to derive the distribution of y equal to negative log x. First notice that this when x is a random variable with the uniform 0, 1, that means all the possible values of x are between 0 and 1, then negative log x takes values in 0 to infinity, positive values including 0 because log 1 is 0. Right. And there also notice that this is a one-to-one transformation. One-to-one transformation from 0, 1 to 0 infinity interval. So therefore, we can now, because it's a continuous transformation, we can now apply the previous result directly. Right. So in order to apply that, we have to write down this thing here. We have to substitute g inverse y. Right. So that means we have to write down, find out x in terms of y. And then also we have to find out the first derivative of x with respect to y. So therefore, we have found out from this one, x is equal to e to the power y, negative y, sorry. And then a derivative of x, you can take the derivative from this function, is equal to negative e to the power negative 1. Therefore, the absolute value of the derivative dx over dy is equal to this thing. So by directly substituting, you can fx x is equal to 1 in this case because x is uniform in 0, 1. So therefore, it doesn't depend on x actually. So that part will becomes 1. And then this quantity, we have to substitute. Actually, I have forgotten to put the absolute value here, right? So we have to put the absolute value and that becomes e to the power negative y. Right. So this thing time the absolute value has to be there. I have forgotten to type it. Right. So that should be this, and that will be equal to e to the power negative 1. So you can see that the density function is equal to e to the power negative 1. That is actually the density function of an exponential distribution with rate parameter 1. So therefore, we can see that y has an exponential distribution with lambda equal to 1. That is the rate parameter is equal to 1. Right? So this example can be considered as a theorem also. If x is a uniformly distributed random variable, standard uniform random variable, then y equal to negative log x has an exponential distribution with rate 1. Let's look at another example. Let x has the Pareto density function given by density function given by this expression here. X is greater than 1. X has to be greater than 1. Derive the distribution of y equal to log x. So you can see that again, this transformation is a one-to-one transformation from the interval 1 to infinity, and then log x goes from 0 to infinity. Right? Log 1 is 0, log infinity is infinity. So therefore, we can again directly apply the formula here to get the density function of y. What you need is we have to write down x in terms of y. Also, take the derivative of that x with respect to y. Both are required. So, first note that the transformation is from 1 to infinity to 0 to infinity. Hence, the above result can be applied. Now note that x is equal to e to the power y, right? Y is equal to log x, therefore x is equal to e to the power y. Therefore, the derivative of x with respect to y is e to the power y. So therefore, absolute value will be the same. So therefore, again, I have forgotten to put the absolute value here. You need to put the absolute value here. Uh, right. So therefore, the density function has to be this expression. But now notice that you have to substitute in the density function. You have to replace x by e to the power y, because this whole thing has to be a function of y. You shouldn't keep any x in here. So therefore, you cannot directly write down fx x here. You have to write down fx and in terms of y. Fx is the name of the function. That will not change, but the argument here is y. So therefore, this argument here has to be expressed in terms of y. So therefore, you have to substitute x equal to e to the power y in the density function to get that. So the density function is theta x to the power minus negative theta minus 1. So now we have to write down this x as e to the power y. Right. So that's what we have there, theta e to the power y, negative theta negative 1. And then take the multiplication with the derivative. So therefore, when you simplify this, you get this expression, and we can identify that as an exponential distribution with parameter theta. Right. So that is also a very interesting result. Okay, I think that is enough to understand the univariate case. Now we will look at an extension of that to bivariate situation. Right. I'm not going to prove the theorem here, but I will just mention the theorem. So let vector x be x1, x2, right? It has two random variables. So it's a vector x. x1 is a single random variable. x2 is a single random variable. We are considering this vector x, and that is, so this is the transpose. So that whole thing gives you a vector. So that is denoted by bold x here. Be a continuous random vector with joint density fx x1 x2. So this again replaces x1 x2, that part here, right? Suppose that y is equal to the random vector y1 y2, defined as y equal to some g of x. Right? Suppose this y1 y2 is equal to some g of this vector, right? When you say g of x, that means g of this vector x means g of x1, x2, but g is also here bold, so that also indicates two functions actually. That also kind of a vector. So that g of vector x, that is the same as this bold g of x1, x2. That means actually two things: g1 x1, x2 and g2 x2 x1, x2. So that this thing contains two components, right? So one component is some function of x1, x2. That function is denoted by g1. Another function of x1, x2. That function is denoted by g2. Right? So that's what we mean by y equal to gx. So let's consider that. And suppose this is from x to y, the gives us a one-to-one transformation. Right. Now, when you write down that, suppose we can find out y1 and y2 in terms of x1 and x2, and that will involve some other functions. I will call it them by H. Right. So here what I have mentioned is this thing in terms of random variable. So y1 is a random variable, that is g1 of x1, x2. X1, x2 are random variables. Y2 is g2 of x1, x2. So assume the following. G is a continuously differentiable. So both g1 and g2 are differentiable. G is one to one on the support of x. Right. So that means whenever you have x1, x2 point, that maps the point into a y1, y2 point as one-to-one function transformation. The inverse transformation exists, right? So we are using a single letter here that is actually the same as G inverse. That is another notation, but to make it simple, we use H, right? So, and also the Jacobian matrix of H is non-singular on the support Y. So those are the assumptions. So let me briefly explain some of these things. So when I say H is G inverse, that means X is equal to HY, right? So we transform X into Y using the function G, and we assume that we can transform Y into X by the transformation H, right? So when you say H of Y, this vector Y, that means H of Y1, Y2. So there are again two functions. H1 of Y1, Y2, so that will be X1, and H2, Y1, Y2, that will be X2, right? So this Y1, Y2 is transformed into X1, X2 by this H. So equivalency in terms of random variables, x1 is equal to h1 of y1, y2, x2 is equal to h2 of y1, y2. Now, what do you mean by this Jacobian? Jacobian matrix H of X. Jacobian matrix of H, function H is this one. This derivative of this function with respect to y1. And then this one, derivative of that function with respect to y2, right? So that's a function. So first take the derivative of that function with respect to y1 and y2. Then this one, this is actually x1. This whole thing is x1. So that is the same as the derivative of x1 with respect to y1, derivative of x1 with respect to y2. And similarly, this is the derivative of this function that is actually x2. So derivative of this function that is x2 with respect to y1 and derivative of that with respect to y2. That is the Jacobian matrix. That is denoted as JH y1, y2, JH. Right? So that is the Jacobian of the transformation H. So what we need is the determinant of that. Right? In the theorem, it says, theorem comes here, right? So in order to get the density, joint density of Y, we want the determinant of JH. So determinant of JH is just this term times this term minus this term times this term, right? This times this minus this times this. So that's what we have here. Then the joint density of Y is given by this expression, Fy, this is the density. Evaluated at y1, y2 is equal to fx evaluated at x1, x2. But now you have to write down x1 in terms of y1, y2. That's why we write down h1, y1, y2, and then x2 here as a function of y1, y2. That is h2, y1, y2. And then this quantity. When you simplify this thing, you can get a positive or negative quantity. What you need is the absolute value of that. Absolute value of this determinant. Right? This is the density when y1, y2 point that we consider here is in the support of y, right? Otherwise, it is the density is equal to 0. The absolute value is required here because generally this can be negative, but finally the density function has to be positive, right? Okay, so that is actually can be seen as a direct extension of the previous univariate case. In the univariate case, we had fy at some y is equal to fx at h of y times the absolute value of dx by dy, right? Here also the same thing. These are dx by dy, dx by dy. This dx1 with respect to by dy1, dy2, and so on. So that can be considered as a direct extension. Right. So now let's look at an example. Suppose that x1 and x2 are independent random variables, each uniformly distributed over the interval 0, 1. They both are standard uniform, independent. Let y1 is equal to x1 plus x2 and y2 is equal to x2 minus x1. Find the joint density of y1, y2 and the marginal distributions of y1 and y2. We will find out marginal densities. Right. So here, just to match with the theorem, we will identify the necessary quantities. Here A, the joint density of x1, x2 is defined from A. What is A? A is just this rectangle. It's actually a square, 0, 1 times 0, 1 square. Now we need to find out express x1 and x2 in terms of y1 and y2, right? So the first of all, we have this, here we have expressed them as random variables, but now I'm writing them down them as mathematical variables, because in the initial mathematical calculations, we are considering them as mathematical variables rather than random variables, right? So y1 is equal to x1 plus x2, y2 is equal to x2 minus x1. When you simplify, when you solve these two equations, we can write down x1 and x2 in terms of y1 and y2 like this. x1 is equal to y1 minus y2 divided by 2, and x2 is equal to y1 plus y2 divided by 2, right? So you can see that whenever x1 for any x1 x2 point, y1 y2 gives you a unique value, right? And for a given y1 y2, you can get a unique x1 x2 value. So what is the set B here, right? When x1 is in 0, 1 and x2 is in 0, 1, x1 plus x2 is going to be in 0, 2. x1, so that means y1 is going to be in 0, 2 interval. y2 is going to be in negative 1, 1 interval. So therefore, we can identify the event B by considering these values. For example, it's better always to identify these two sets, A and B, especially if you want to find out the marginal densities later on. You'll have to integrate the marginal density, joint density with respect to y1 and y2. And in that case, to find the limits, it is important to notice what is the domain, the support actually, support of the joint density of y, right? So therefore, it's always good to look at this A and B, right? So in order to identify A and B, we will look at the boundaries of set A, and then to what lines or curves those boundaries convert by the transformation, right? So here, this is the set A, 0, 1, 0, 1. This is the square. Now we will see to which curves or line these boundaries are converting. Right? So this is x2 equal to 0. So when x2 is equal to 0, y2 is equal to negative y1, because we have expressions x1, x2. So when x2 is equal to 0, we get y2 is equal to negative y1. Right? So that is x2 equal to 0 line now is converted to this line. And similarly, x1 equal to 0 line, x1 is equal to 0 line is converted to y2 equal to y1 line, y2 equal to y1 line. Right? I'm expressing all these things for y2 because I'm going to consider y2 as my vertical axis and y1 as my horizontal axis. Therefore, it's easy to draw the lines when you consider y2 as my y axis and y1 as my x axis. And the other two lines are x1 is equal to 1 and x2 is equal to 1 in set A. So those are converted into, say, for example, when you put x1 is equal to 1, you get y2 is equal to y1 minus 2. And when x2 is equal to 1, you get y2 is equal to 2 minus y1. Right? So therefore, you get these two lines. Now, B will be bounded by these lines. So when I draw these lines, y2 is equal to y1, y2 is equal to negative y1, y2 is equal to y1 minus 2, and so on. You get this picture. So this our transformation is going from any point in this set to this set. So now let's find out the Jacobian. Right. So in order to find out that one, we have to differentiate x1 with respect to y1 and x1 with respect to y2, and then x2 with respect to y1 and x2 with respect to y2. So when you take the derivative with respect to derivative of x1 with respect to y1, you get 1 half. The next one will be negative half. When you take the derivative of x2, you get positive half and positive half again. So therefore, right. So these are the values in the matrix. Now you want to look at the uh, uh, determinant. Determinant is going to be this times this minus this times that. So that will be 1 half. That is positive. Otherwise, if it was negative, then you'll have to take the absolute value of that. Right. So all the assumptions are satisfied. We can check them. And therefore, the joint density function of x1, x2, right? Because this is both x1 and x2 are independent. They are uniform. So therefore, the joint density function of x1, x2 is going to be the product of the marginal densities. So that is going to be 1 times 1, right? x1 has a uniform density. That's therefore the value is 1. x2 also has a uniform density in 0, 1. So therefore value is 1. So therefore the product is 1. So this is the uh, joint density of x1, x2 for any x1, x2 in set capital A. Now, therefore, using the formula, we can say the joint density of y1, y2 for any simple y1, y2 in set B as 1 times, right? So we apply this formula. This part is 1 and then this one is half. So therefore, we get this expression. It's half. So it's also a constant. But on now on, this rectangle here, right? Okay. Uh, the height of the joint density of x1, x2 is 1 over this region. Height of the joint density of y1, y2 is just half over this region. That is because the area here is 1 and the volume becomes 1 when the height is equal to 1. But the area here is 2. And therefore, for the volume to be 1, it has to be a height half. Okay. Now, suppose you are also interested in finding out the marginal densities of y1 and y2. So if you want to find out marginal density of y1, y2, y1, for example, you have to differentiate with respect to integrate with respect to y2. And in order to get the marginal density of y2, you have to integrate the joint density with respect to y1. Right. So now let us look at these two separately. I have the expressions here. I have first got the marginal density of y1. Right. So that means let's consider this picture again. Right. So now I want to get the marginal density over this line here. Right. Now you can see that you have to, you will see that the marginal density has to have two parts. Because if you are considering your y, say simple y1 value, simple y1 value anywhere here, the marginal density you can get by integrating the joint density with respect to y2 over from here to here, right? So for any value here, it will be like that, similar up to here. And if your y1 that you are considering, you are going to calculate f capital Y1 evaluated at say simple y1. You don't have to put y1, you can put y if you want, but we will use simple y1 to destination. Right. So if I'm considering this y1 to be any value between 0 and 1, then uh, f y1 evaluated at that y1 when y1 is between 0 and 1, this will be equal to integration of the joint density of y1 and y2 with respect to y2 from what to what? From this point to this point. So what is the value of y2 uh, at this point? That is going to be negative y1. And what is the value of y2 at this point? That is y1. Right? So that's what the density function of y1 at simple y1 when y1 is between 0 and 1. If your y1 is between 1 and 2, right? When y1 is between 1 and 2, right? You can include 1 here, doesn't matter, right? So in that case, f y1 at that simple y1 is equal to again the integration of the joint density fy1 y2 evaluated at y1 y2 now with respect to y2, but y2 now has to go from some point like this to this y2 point. So y2 here is y1 negative 2. Here y2 is 2 minus y1. So therefore this has to be y1 minus 2 to 2 minus y1. Right. So you can see that when you integrate with respect to y2 and put the limits, then this is going to be a function of y1. And similarly here. Right. So that's how you get the marginal density of y1 in this example. And similarly, if you want to get the marginal density of y2, you have to integrate with respect to y2. Now again, you can see that marginal density on this axis. Again, you can see if you consider y2 value to be somewhere here between 0 and negative 1, you can integrate the joint density with respect to y1 from this point to this point. So in that case, y1 will be negative y2 to y1 will be y2 plus 2. y1 is changing from negative y1 to y2 to 2 plus y2. Right. If your y2 is somewhere here between 0 and 1, you will be integrating over a line like this. So in that case, taking the derivative with, taking the integration with respect to y1 from here to here. So y1 is equal to y2 here. Y1 is equal to 2 minus y2 here. So therefore, those limits have to be applied. So I have done that and obtained the expressions. So you can see that it has two parts. When y1 is in 0, 1 interval, it's given by this. When y1 is in 1, 2 intervals, going by this, actually, the border point, you will get the same answer, right? When y1 is equal to 1, 1 value is 1 here. If it's value 1 here, same. Therefore, you can exclude that point from one region and include that point in the other region. It's a continuous function anyway. And similarly, if the density function, marginal density of y2 is given by this expression, again it has two parts depending on simple y2 that we consider here. Right. Now let us look at another example. This example is coming from the book. This is the example 3.63. Let x1, x2 be independent exponential random variables, independent exponential random variables with rate parameters lambda1 and lambda2. For a constant a greater than 0, define y1 to be x1 and y2 to be x2 divided by a times x1. Right? So what we want to get is the joint density of y1 and y2. Right? So what we need here is to again see that this is a one-to-one transformation. Right? X1 and x2 are independent random variables. X1 is in the interval 0 to infinity. X2 is also in the interval 0 to infinity. Right? So y1 is also from 0 to infinity, and then y2 is also from 0 to infinity. Right? Uh, the inverse transformation, that means we need to find out x1 and x2 in terms of y1 and y2. So x1 is equal to y1, and from this again get x2 is equal to a times y1 y2. Right? From these two we can easily get this. And then we need the Jacobian. For the Jacobian, we need the derivative of this with respect to y1 and derivative with respect to y2. The same thing, that will be the first row. And then derivative of x2 with respect to y1 and derivative of x2 with respect to y2. That will be the second row. So that will give you these values. And when you take the determinant, it's going to be 1 times this minus this. That is a times y1. So y1 is always positive here, therefore this is positive, right? No need to consider the absolute value here. So therefore, if you directly apply the formula, you get the joint density of y1, y2 is equal to, okay, so how did we get this one? I will write down first of all, I will write down the joint density function, then it will be easy to understand. The joint density function of x1, x2. Evaluated at x1, x2 is going to be the product of individual exponential densities because x1 and x2 are independent. So it's going to be lambda1 e to the power minus lambda1 x1 times lambda2 e to the power minus lambda2 x2. So that is lambda1, lambda2 e to the power minus lambda1 x1 plus lambda2 x2. So now when you're substituting here, this has to be f x1, x2, x1, x2, of course, but this has to be replaced by y1, y2, some function of y1, y2. This has to be replaced by y1, y2. So therefore, this function we have to put, but we have to substitute x1. x1 is equal to y1. X2 is equal to a times y1, y2. Right? So that's what you have here, lambda 1 by 2. And then this a y1 part is coming from this. That's the Jacobian. Right? Uh, the determinant of the Jacobian. Right? So you get this expression. Let's look at another example. This is again coming from the book. Example 3.64, ratio of two standard normal random variables. So this will give you an interesting result, and you can consider it as a theorem also. Let x1 and x2, let x and y be independent standard normal random variables. Independent again, standard normal random variables. Define u to be x divided by y. And suppose we are interested in actually finding out the distribution of the ratio, but of course, we cannot directly find out that. We have to first find out we have to first consider a transformation from xy to some other two random variables, right, like u and v, and then get the joint density of u and v, and then find out the marginal from that. That's what we have to do, right, generally, right? So therefore, you have to select a suitable. Suppose this was the only function given, then you'll have to choose a suitable some other function of x and y so that the transformation will be one-to-one. And also convenience, right? So you can select the second variable according to the convenience, right? So therefore, I have selected here v equal to y, then actually we can write down x. So y will be a very simple function of u and v. And x also can be written as very easily u times v in that case. So therefore, I have selected v to be y here. So then the inverse transformation is x equal to u times v and y equal to v. And then the Jacobian, first of all, we have to find out, and then here we have found out the determinant. Determinant is going to be absolute value of the determinant going to be absolute value of v here. So therefore, when you substitute the terms, right, first of all, you have to get the joint density of x1, x2, right? So the joint density of x1, x2 in this case is the product of individual, in this case, not x1, x2, we have x and y, right? So the joint density of x and y will be the product of the two densities because x and y are independent. So this will be 1 over root 2 pi sigma is equal to 1 e to the power minus half x square, x minus mu rho. So that is the density function. And then you have to multiply that by 1 over root 2 pi e to the power minus half y square. Right. So now in this expression, you have to substitute x and y, right, by the corresponding inverse transformation. So you have to write x equal to uv and y equal to v. Then you get this expression here, and then multiplied by this quantity here, absolute value of v. Why absolute value of v is important here? Because v is equal to y, where y is standard normal, which can be a positive or negative, right? If it is positive, of course, v will be just that value. But if v is negative in that case, what you have to have here is the absolute value of that quantity. So that gives you the joint density of u and v. You get this expression by substituting the corresponding expressions in terms of u and v for x and y. Right. So if you want to get the density of y now, you have to integrate the joint density with respect to v. Right. So v is equal to y, where y is standard normal. Therefore, it's from negative infinity to positive infinity. So therefore, v is also from negative infinity to positive infinity. Therefore, you have to integrate this joint density function with respect to v from negative infinity to positive infinity. And this is what you get when you do that. Right. So this is again a well-known distribution, the density function of a well-known distribution called Cauchy distribution, which is the same as a T distribution with 1 degree of freedom. Right. So therefore, this result is important. If you look at the ratio of two independent standard normal random variables, the resulting random variable has a Cauchy distribution. Right? Cauchy distribution is an example where a Cauchy distribution is again symmetric around zero, and it's a distribution which doesn't have finite mean and finite variance, finite moments. Right. Okay. So let's quickly look at another example. Let xi, where I from 1 to 2, have gamma distributions with parameters ni and lambda. So that means x1 has a gamma distribution with parameters n1 and lambda. Second, x2 has a gamma distribution with parameters n2 and lambda, and assume that x1 and x2 are independent. Find the distribution of y equal to x1 divided by x1 plus x2. Right? So here in this problem, we need to find the distribution of y. Right? Another random variable is not given. But generally, we will have to first consider a transformation from x1, x2 to say y and some other, say w or something. Right? First of all, consider transformation, bivariate transformation, one-to-one transformation, and then get the joint density of uh, the second pair, and then integrate with respect to the other variable to get the marginal density of y. That is the procedure. Right. So in order to apply the transformation technique, we need to select another function of x1 and x2. So you can select a suitable function, but again, for the considering the convenience, I take this part, this random variable to be the second random variable. So I call it y2, right? So therefore, I will call this y1 now, right? Y1 and y2. Here you have x1 and x2. So y2 is x1 plus x2. Then we can see that that transformation is one-to-one. And then what you need is first we have to get the inverse transformation. That is, we have to find out x1 and x2 in terms of y1 and y2. We can easily do that. Then we get these two expressions. X1 is equal to this and x2 is equal. So here x1 is going from 0 to infinity. X2 is also going from 0 to infinity. Y1 is equal to x1 divided by x1 plus x2. So that is also from 0 to infinity. And y2, x1 plus x2, that is also from 0 to infinity. So this transformation is one-to-one. The joint density function of x1, x2 is the product of individual densities. So that's a product of two gamma densities, and this is the expression. And Jacobian we can find out similarly. I'm not going to spend too much time on that. We can show that the Jacobian is equal to y2 here, where y2, because these are all positive random variables, this y2 is also positive. Therefore, we don't have to separately take the absolute value. So therefore, the joint density function can be obtained as this thing, and then substituting these expressions x1 and x2, x1 is equal to y1, y2, and x2 is equal to this expression in the joint density function here times y2. And that gives you this. Right. Now, what we need is the marginal density of y1 here. Right. Now, usually we'll have to integrate this joint density with respect to y2 to get the marginal density of y. But in this case, we don't have to do that. If you carefully observe this, you can see that this function can be written as a product of two terms where the first term is only a function of y1 and the second term is only a function of y2, right? So that means this y1 and y2 that we have considered are actually independent, right? So therefore, whatever the expression of y1 uh, should be proportional to the density function of y1, right? So I have just written down a constant times this and constant times this, right? So this part helps us to identify the form of the density function of y1. So the density function should have the form of a constant times this expression. But here, this one, we can identify as a beta distribution, right? Coming from a beta distribution, y1 to some power minus 1, 1 minus y1, some power minus 1. So that is the form of a general beta distribution. So therefore, this constant has to be the constant, constant of normality, right? Not normality, normalization constant of a beta distribution, right? So therefore, very easily we can identify that the marginal density of y1 has to be a beta distribution with parameters alpha equal to n1 and beta equal to n2, right? So therefore, this is an example where you don't have to really integrate, even though you integrate this part when you're integrating with this full and that part will be completely one, and therefore the other part will, right? Okay. Now let us look at a different situation. There are situations where the transformation that we consider is not one to one from whole area A into B, but we may be able to consider the transformation as a combination of several transformations, one-to-one transformations from some subsets of A to B. We will look at an example like that. So we say it transformations with several inverse branches. If the transformation is not one-to-one, but has finitely many differentiable inverse branches, say G1 up to Gk, then the contributions from all valid branches must be added to get the joint density of y's. Only branches whose inverse points lie in the support of x are included in this case. So that means when you consider a point in y, that is point in B, for example, capital B, and if you consider the inverse transformation will go to several possible points in A. So from those each point in different subsets of A to point y in B can be considered as a one-to-one transformation. And then we'll have to consider all those separately and find out joint density and then add them up to get the overall joint density. That's what this means. So let's look at an example. A transformation with four inverse branches we are considering here. Suppose x1 and x2 are independent random variables, each uniformly distributed over -1 to +1. Their joint density is given by then 1 over 4, where x1 is between -1 and +1, x2 is between -1 and +1. Right. So then the set A is the square with each side has length 2. So therefore the total area of capital A is 4. Therefore the height or the uniform distribution should be equal to 1 over 4. Now, let us consider the transformation y1 is equal to x1 square and y2 is equal to x2 square. What we want is to find the joint density of y1, y2. Now, in this case, clearly, the transformation from x1, x2 to y1, y2 is not a one-to-one function. X1, x2 can be any point in capital A, where capital B is, again, it's a square with one side 0 to 1, the other side is 0 to 1. So the transformation is not to 1 because the signs of x1 and x2 cannot be recovered from y1 and y2. Right. For a given y1, y2 point, there are 4 possibilities of x1, x2. Right. So, for example, let us consider any y1 between 0 and y1 and y2 between 0 and 1. Then you have corresponding to that y1, y2 point, you have this scenario. For example, let us consider y1 is equal to 0.36, y2 is equal to 0.64. I have considered them just to make it easy to take the square roots. Then the corresponding x1, x2 can be either this point or this point or this point or this point. Here, for example, x1 can be plus or minus 0.6. Therefore, x1 square will be 36. x2 can be plus or minus 0.8. So, x2 square can be 0.64. Right. But if we consider the transformation from this to this, 1 to 1. Transformation from this to this, that is 1 to 1. Transformation from this to this is 1 to 1. Transformation from this to this is 1 to 1. And similarly, the inverse transformation from this to this is 1 to 1. Inverse transformation from this to this point is 1 to 1. Inverse transformation from this to this is 1 to 1. And so let's consider those inverse transformations. Right? Inverse transformations are denoted by H1, H2, H3, H4. So if you take any point y1, y2, like the one that we considered, then one transformation can be going from y1, y2 to root y1, root y2. So that will be from here to here. Both values are positive. And similarly, another one is root y1 to negative root y2. Right. So that will be something like this. Yeah. And the other one is negative first value and say positive second value. That can be something like this here. And the last one is this. Right. So each inverse transformation is 1 to 1. Right. So therefore, considering each, we can find out the joint density. And then final joint density will be the sum of those joint densities. Right. So if you find out for each function, each inverse branch has the same absolute Jacobian given by this thing. You can easily calculate that because we are considering the absolute value. Absolute value will be the same. The joint density of y1, y2 is obtained by adding the contribution from the 4 inverse branches. Right. So therefore, the joint density of y1, y2 will be the sum of the joint densities coming from each branch. Right. So that is going to be 4 times 1 over 4 because each term is in this case equal. 4 times 1 over 4 is the joint density of x1, x2. And this is the absolute value of the determinant of the Jacobian. So this is the function. So therefore, this is the more complete answer. The joint density of y1, y2 can be given by this expression if y1 and y2 are in this capital B set, otherwise C. So that is an example where how we can solve a problem when the transformation is not one-to-one from A to B, but especially the inverse transformation from B to A is not one-to-one. It can be one-to-one from B to A, B to A1, B to A2, B to A2, B to A3, and B to A4 like that, and then consider individual inverse transformation separately and get the density, joint density, and add them up to get the overall density. So we can actually, if you want, you can check whether it is actually a proper density. In order to check that, you can integrate the density that we got, integrate the function that we got with respect to y1 and y2, and then we see that is equal to 1. So therefore, it's a proper density. So that is the end of this video and this section. In the next video, we will discuss about copula and copula method to generate data.